it's a nice relaxed pace, right? So, and there will be some questions on this chapter. So if you're ready, we'll get started, right? Chapter 21, right? Okay, like I said, we'll go through this chapter. It's a short chapter, but there's 4 nice examples at the end. And then we will have our final exam review. Okay. And we'll wrap up the course, right? Okay, so starting with chapter 21. Now, we are talking about in this chapter 2 samples. So that's from 2 samples from 2 different populations. And this is very common in practice because quite often you want to have a control and a treatment group, and you can compare the 2 groups. Remember how in the last chapter we did way back 2 weeks ago, we did diet and exercise. We compared, it was one study where they were doing a diet and then looking at exercise and which group of participants lost the most weight. You don't have to construct a confidence interval for each like we did. You can, but even better is to do one confidence interval where you can see the difference between the 2. So it's a way to compare 2 population means. We're going to just do means in this course. That's all we have time for. And the 2 sample T procedures, that's the same thing. And then talking a little bit about robustness. These are really good tests, the confidence interval and the hypothesis tests. And then the T approximation, that's our table. Okay, so it is one of the most common situations encountered in statistical practice. We just call them 2 sample problems, 2 sample t-test, 2 sample hypothesis test, just 2 sample, because we are getting 2 samples from 2 different populations. And I think I should have a picture. No, I don't have a picture. Okay, so we're comparing the difference between 2 means. And because we have 2 populations, we need some subscripts, meaning these little numbers right here at the bottom. Let me grab, I need a color here. There we go. So we have these subscripts, 1 and subscript 2. And that's a way to distinguish between the 2 samples. So from population 1, mean the mu1, that's what we're trying to estimate, and mu2 from population 2. And we usually look at their difference. So the difference means you subtract one from the other. And their independent population means, and it looks like, I want to get to the formulas soon. Yeah, the conditions, we should go through the conditions, make sure that how we're doing this. So we are assuming that we are taking simple random samples from each of those populations. Both we assume to be normally distributed, unknown means, standard deviations. But even though it's normally distributed, we use for all of this chapter, always the T distribution. Okay. In practice, it is enough to say the distributions have similar shapes. And we want to make inferences about the difference. So here's the difference right here. We usually put brackets around them. Right? So mu1 is the mean of the first population. Mu2 is the mean of the second population. Right? And this is what it looks like. This is the t-test statistic. So you can see we have mu1. So there's the bar, mu sub 1. So there's x bar subscript. Remember, those subscripts go for which population you're talking about. So x bar subscript 1, subtract x bar subscript 2, subtract the differences of the 2 means. And then the denominator, we have our variance, right? Variance, so that's going to be subscript 1 with the s. And the subscript 2, that's the variance for the variance for population 2. And we even have subscripts for the sizes because they might be different, right? You might have say 20 observations from population 1 and 21 observations from population 2. Sometimes they don't have to be exactly the same. So they can be different. The question is when we do something like this and we're using the t-distribution, what degrees of freedom should we use? Right? So we used to just take, when it's one sample, we would just take n and subtract 1, right? That would be our degrees of freedom. But when we have two n's, what do we use? So what we can do is we could use this formula, which we have not used in several years. When I first started teaching this course, this formula used to go on the exam, and it was just a mess because we ended up realizing we were testing the wrong thing because it's so easy to make a mistake with this formula. So that's what the software, we just call it the software formula. We won't be using this on the exam. Instead, what we do is this option 2, where you take the smallest n and you subtract 1. So if n1 is 20, and n2 is 21, then you just take 20, because that's the smallest of the two, and subtract 1. So the degrees of freedom would be 19. So you take the smallest. So without the software, we use the smaller of the two, and this works really well. Like, it sounds like, we're kind of bypassing the software sophisticated formula, but it still works really well for our purposes, gives us really good estimates, right, from the table. And we call that the conservative approach. So you'll see with the examples how we do it. All right. So we don't have software for the exam, we use that. This is what the confidence interval looks like. And it's really good to have brackets. Make sure you take the difference. And do you notice the structure, right? It's some estimate plus or minus the margin of error. In our case, we have some estimate is the difference between the X bars, the averages from our samples. And we have our T star, that's from the table. And you'll take the smaller of the n and subtract 1 to get the T star, the minimum value. And then we have this square root. Because we have two populations, we're going to have two variances in that square root with two n's. And you just have to be careful putting all that into the calculator. But it's all given to us in the question. And you plug those in and you get your confidence interval. So a two-sample confidence interval for the difference, mu1 subtract mu2, the true difference, right, the difference of the populations, is based on this formula. And you will have it on the formula sheet, which I believe I've already posted. It's on Brightspace, so you have all your formulas that you know that you'll have. You don't need to bring the formula sheet. It's being printed, so it will be printed, and so will the two tables. Okay, so you'll have a formula sheet provided for you, the normal distribution and the t-distribution to construct these confidence intervals. So you just take the smaller one and you subtract 1, and then you have this really neat. And the examples from this, even the textbook, you'll see how, oh wow, this is really useful. Like, we use these a lot. So studying two different populations, I literally have taken from one of my PhD advisors, one of his examples. It literally is two populations. We have the native Italians and the Etruscans, which they've found several skulls, bones, right, in Italy, and they want to know if they were, the question is, were they, from that region? So they compare the skull measurements of 84 Etruscan males to 70 modern Italian males to examine the question. So it's an ancient civilization. And the question is, were ancient Etruscans native to Italy? So they can take these measurements from literally two different populations. We take we did the box plots. It's always good to plot the data. You can see visually, we're pretty suspectful that there's a difference here, right? You can see the skull measurements for the Etruscan males were much higher. You can see they have higher measurements based on the y-axis there. There's an outlier for each population. And the Italians are lower, smaller skull sizes. So measurements. So we're already suspectful that there will be a difference in the measurements. How do we know? We collect the data. So here's the skull measurements. We have one was the Etruscans. So the average measurements for the Etruscans was 143.77 compared to the modern Italians, which was 132.44. We can see those, we're now really becoming suspicious. There probably really is a big difference between the two. And then if there's a difference, then they may not be native to Italy, right? If there's a big difference. Then we have our standard deviations. They're pretty close, 5.97 and 5.75. And then we have our sample sizes. So we had 84 Etruscans and 70 Italians. We have all the data we need, except for the t. We need the t-star if we're constructing a confidence interval. So using the software, that really elaborate formula, it ends up being 146.3 degrees of freedom. You can have decimal place degrees of freedom when you use the software. So we plug all the values in. So that was x bar subscript 1, subtract x bar subscript 2, and plus or minus all the rest. It's literally just being substituted in. The only difference between these two confidence intervals is one is using the software approach, that's the t here, and then this one's using the t for the conservative approach, which would be 69 degrees of freedom, right? Because you take the smaller n, so you take the 70 and subtract 1 is 69. Gives you 1.9949. Okay, and does it keep going? It doesn't keep going. So it's just showing you what those differences would be. In the red is the final, and you can see that it does not contain 0. So what you look for is there a 0 in the range? And no, there's no 0. So this means that we conclude that there is a difference. There is a statistically significant difference between the two sizes. If 0 was in the range, then we'd say there's no difference. But 0, right? If 0 was in, we'd say there's no difference, but it's not. So if both your numbers are positive, your min and your max, or if both your numbers are negative, then you have a difference. It means there's a significant difference between the two populations. So we conclude there's a significant difference between the two populations of the Etruscan measurements and the Italians. And what do we say? Well, I think I have a bit more to say in a few slides. So we do the same thing with the hypothesis tests, right? We have our null and our alternative hypothesis tests. It's done exactly the same way as before, except for we have the null hypothesis is where the means are equal, right? Or if you bring one over to the other side, just like algebra, you say the difference is equal to 0. And here, for our purposes, it's always 0, 0. And then you have your alternative hypothesis, case 1. You could have not equals, case 2. You could have less than, 0, or case 3, you could have greater. So this would mean that the difference is less than 0, or the difference is greater than 0. So it's negative or positive, or does not equals. So we have a two-sided test or a one-sided test. Okay. And you just plug those in. The test statistic just looks like that. Again, for degrees of freedom, take the smaller of the n and subtract 1, and you calculate the test statistic, right? So step 1 is the null and alternative hypothesis. Step 2, calculate the test statistic. Step 3, get the p-value. And step 4, make a decision based on the alpha. And our alpha is usually 0.05. Usually, it can be anything, but in most tests, it's 0.05. So if we look at the Etruscans, our null hypothesis is that the skull measurements are equal, or another way of writing it is the difference is equal to 0. The alternative was they're not equal, or the difference is not equal to 0. So this means no difference. And this means there is a difference. And then we calculate the test statistic. We get 11.97. We're using 69 degrees of freedom. We go through the whole process. We look and go, well, what's the p-value? The p-value, we're using software here, but even with the table, the p-value is right off the page. It's this number times 10 to the minus 19, really, really, really small. So that means there is strong evidence against the null hypothesis. And we conclude there is a difference between the two populations. The result is statistically significant. And so when we do this, we compare it also to the confidence interval. We had the same result with the confidence interval, right? The confidence interval said there's a difference because 0 wasn't in the range. And so we reject the null hypothesis and we accept the alternative, right? So we reject the null. That means reject. Strong evidence against the null means we reject the null hypothesis. So we're accepting that there is a difference. Okay, so that's using the Etruscan example. Right, so it's very similar to everything we did in chapter 20. We're always using the t for these questions, right? We only use z when we know the population standard deviation, right? So, but for all these, it's all t. Everything in 20 and 21 is always t. So here's the slide I was saying. Even though we statistically say that there's a significant difference between the measurements of the two populations, the Etruscans and the modern Italians, does the analysis really show that the Etruscans were not native to Italy? We can't 100% say no, because there are too many lurking variables, such as the Etruscans' skulls were ancient. The Italian skulls were modern, so they're different there. Changes in diet could explain that, right? Ancient to modern times, different food, different nutrition, we know that has an effect. Environmental changes between ancient to modern plays a role with our size. And also our modern Italians, really immigrants themselves from the time of the fall of the Roman Empire. So this is still ongoing research. So whenever they have, it's in has anyone taken anthropology? It's good, right? The biological one? Which one? It's good, yeah. Yeah, anthropology, it's, if you have room in your schedule to take that sometime as an elective, it's great. They're great courses. Really, you learn so much about people in both the biological and the cultural anthropology courses, the first year courses. Robustness, yes. They're less sensitive to departures from our conclusions, so they're good. This means they're good. They're robust. That means they're good. They hold up for even if you deviate from the conditions. When both the sample sizes are equal and both sample distributions are similar, but even when you deviate from this, they still can be trusted. The results can still be trusted. It's good. Quite robust in that sense. All right. So in Ontario, another example that I've used for many years, we have lots and lots of trees, London especially, right? The forest city. And we have a lot of trees that cost a lot of money to be trimmed because if they get growing into the hydro lines or just getting onto the roads, right, for garbage pickup and all this. So what they do is you can see here, 1995, they trimmed 500,000 trees in Ontario for $25. This is in 95. So imagine what it costs now. So what they do is they did a test to see if we spray them, we can slow the growth down of these trees with this toxic chemical. I'm not sure if I think it's still being done, but so they have measurements that they did on the internodal lengths of the branches and to determine the effect of the sprays. So this chapter is about comparing two population means. Can you kind of tell where I'm heading with these trees? So some trees are going to be sprayed, right? And then some trees will not be sprayed, right? So we'll have a control and we'll have a treatment. And then what they did to see if the spray really does have an effect, they can then see if it's worthwhile doing to save the money, and then they don't have to cut as often. So here's the tree data. So one without the chemical control injection, that's the control. It's without the spray. So one is without, and then the treatment is when they are injected with whatever that is. It's that chemical that they use. And one branch from each tree is chosen, and each with 11 internodal lengths. So we have a control tree branch and the treatment tree branch. These are the measurements. So if you were to add them all up and divide by 11, each with 11, that's our N1. So N1 would be 11. N2 would be 11 as well. And if you add them all up, divide by 11, you'll get for the control 4.191 as the average length. And for the X2, 2.155. And then you could calculate the standard deviation that for each population. Remember that? That's way back from chapter 2. So you could do that for each. But it's given to us to save time. And you can then calculate a confidence interval or a hypothesis test to really see, is this worthwhile? Is it worth the time to doing these injection sprays, or should Ontario just keep letting the trees grow at the natural pace? So here's the data. If you look at the data, we do see without, they're much bigger trees. The distribution's the lengths are much higher, longer, if you will. And then the treatment, looks like they're slowing it down. They're slowing down the progression of their growth so that they don't need to be trimmed. The whole idea is to save money from the trim. And so we can do the hypothesis test. So step 1, the null and alternative hypothesis. So the null is always equal. So that means that they're equal. That means no difference. No difference in the average between the control and treatment. This means that the alternative is that the greater, or another way to write this is mu1 subtract mu2 is greater than 0. And another way to write this one is mu1 subtract mu2 is equal to 0. These are other way, just another way to write it. It's just algebra. So they're equal or their difference is equal to 0 versus mu1 is greater. That means the ones without the injections, right? That without the injection sprays is they're greater lengths than mu2. It's what they want to know. And so the difference would be greater than 0. And then the calculate, just plug in the measurements from the data for the test statistic. And because we have 11 in each group, the degrees of freedom would be 11 minus 1, 10 degrees of freedom. And that corresponds to a one-sided p-value between 0.025 and 0.05. We'll get in, when we do our examples, we'll have our table ready to get that. Using software, the p-value is exactly 0.026. So we have a small p-value, it's less than 5%, and we conclude that the control group is greater than the treatment group. So we reject the null hypothesis, and we conclude that there is a difference, right? Because so the p-value is less than sigma, which is equal to 0.05. Whoops. So we reject. We reject the null hypothesis, and then we conclude that the control group is greater than the treatment group, indicating the chemical injections used significantly reduced tree growth. So I'm not sure they still do this. I wouldn't be surprised if they do, because it's a lot of money and it's much cheaper to do that. But then there's been a ban on those kind of chemicals. They get into the waterways. So I'm not really sure what they're doing. I could check into that, see what's happening. But yeah, I tried to get a variety of examples, the Etruscans example, the trees, and I have 4 more, right, coming up. So we'll work through these questions here, right? Does anyone have any questions before we do the last examples? We have 4 examples. I told you it's a short chapter, nice and short. Finish up the course quickly. Right. All right, so this one here, now in chapter 20, I talked about there was a study where they were comparing a diet and exercise with different participants in each group, right? We had 42 men in the diet group and 47 men in the exercise. And what we did in that chapter is we constructed a confidence interval for the diet group and then a separate confidence interval for the exercise group. Here, we're going to roll the data into one confidence interval. And we'll just compare the difference. So we will take population 1 and subtract population 2, and we'll calculate that 95% confidence interval. So it's going to look like this. So a 95% confidence interval for mu1 subtract mu2. So that's think of that in words. That's the difference between the average weight loss between the diet and the exercise. That's all wrapped up in mu1 subtract mu2. So the average difference between the weight loss between the diet and the exercise. So we say is, and it's going to be this. So it's going to be x bar 1 subtract x bar 2 plus or minus the standard deviation, which is going to have a t star, times the standard deviation, the standard error. Now, I usually do the standard error separate. You can put it all into one, but it's just a little bit easier to do the standard error separate because it's got that square root. So well, it doesn't really matter. I guess we could throw them. The standard error is equal to s squared 1 over n1 plus s squared 2 over n2. So that's going to be, I'm just doing this on the sideline because I think it's easier. So that would be 3.7 squared divided by 11 plus 3.9 squared divided by 11. Now be careful, if you're already, if these were, if S1 and S2, if those were squared, then we would just put the numbers in without squaring them, if they were already squared, right? Yeah. Divide by 11 because, oh, right, I'm thinking of the tree still. So it should be, good catch. So what should be the first one? Yeah, good. 42 males in the first diet group, right? I gotta switch gears here. Diet and exercise. And the second group? What should I put in the denominator for the second group? 47, yes. Good catch. Thank you. And we're gonna get our calculators and we'll work together to grab this number. Make sure it all stays in your So this is just sort of along in the margins. I do this sort of separate in the margins. Just, I should probably carry a few more decimals since I'm going into, this is an intermediate step. Unless the question literally said, what is the standard? Let's do 6. Let's do that. Unless the question says, now if the question says, what's the standard error of the estimate? This is your answer, right? SE stands for, you can make a note of this, SE stands for the standard error. The standard error of the difference of the X bar subscript 1 subtract X bar subscript 2. So that could be a question right there. And then we need to also get the T. Let's put in the difference. So you guys can help me along here. Make sure I don't write anything wrong. So that would be 7.2 subtract 4.0 plus or minus. Everybody's okay with that? We now need to go to the table. And how many degrees of freedom do we want to use for this question? We need a T. We only want to get one T, but we want to use the conservative approach, and we want to get a degrees of freedom for the table. Yeah. 41. Yeah, 41. Now what we could do, because we don't have a 41, if you remember back to chapter 20, I think we ended up using 40. So we'll use 40. That says use. And so let's go over here, because you'll see here, we don't have a 41. So we'll use that one. And we want 95. And so we'll use that one right there, right? We only want one T, so we have to just choose the lower of the two. We have 42 participants and 47 participants. You take 42, subtract 1, gives us 41, but we don't have a 41, so we'll take a 40. It will be close enough. It will be really good still. 2.022 sorry, 2.021. That's our test. That's what we're going to use. 2.021. And then times our SE, well, we already have that. It's 0.806. Try to carry at least that many. I've rounded because it really went into 0.595 or something. So this should give us good, carry at least three for your intermediate steps. And then I can then go equals. That's going to be, I'm just going to go 3.2 plus or minus 2.021 times 0.806. I get for a margin of error 0.62, I'll just call it 63. So this is the margin of error. Let's just grab green and make sure we know that this, the margin of error, is 1.63. All right. The standard error over here is 0.806. So we know the standard error, we know the margin of error. The margin of error is when you take the standard error and multiply it by our T star, right? And then our estimate's 3.2 plus or minus 1.63. We can unravel that to get a minimum and maximum as well. And we get this. Two. There. So our confidence interval goes from 1.57 to 4.83. So then you go, okay, that was the weight loss. That's the difference in weight loss. We can put a unit to it because I believe it was kilograms, right? So it's kilograms. So what does that mean? Is there a difference? Is there a statistically significant difference? (1.57 to 4.83), they're both positive. There's no zero in the range, right? There's no zero. So that means there is a statistically significant difference between the two weight losses. What? Yeah, this. So this is the difference between diet and exercise. So because it was the average of the diet first. So on average, the diet lost more, right? 1.57 to 4.83 kilograms more than the exercise. And because there's no zero, we can say that there's a significant difference between the two weight loss methods. Right? So zero is not within the range, like the interval range. We say there is a difference. There is a difference between diet and exercise. Yeah. It's close, but no, it wouldn't count as zero because it's positive. It's over the zero. So like if you go from, if it was negative 0.57 to positive 4.83, then you have zero in there and you would say that there's no difference. Does that mean, yeah, that would mean that there's no difference between the weight losses. Yeah, I can do that. Then you would say there's no difference. You would still say there's no difference. Yep. Yeah. So that's how it's done. That's two sample confidence interval, we call it. Yeah. Yeah, sure. So we have an N1. Let me just highlight these. We have N1, which is 42, and N2, which is 47. So we have 42 men in group one, in the diet group, 47 men in the exercise group. And the conservative approach for the two samples is you take the smaller of the group, which is the diet, that's 42. You take the smallest of the group and you subtract one. So we would have then 41 degrees of freedom. So based on that, we would do this. We would say that so this is the smallest, and we would go 42 subtract 1 equals 41 degrees of freedom. And there's no 41 on our table, so we will always round down. Yeah, so we round down to 40. Yep. Always round down for your degrees of freedom. I think well, it is. It's safer because you're taking the smaller t when you do that. We could have rounded up, but it's a smaller t, sorry. It's a smaller t when you round up. It's larger when you round down. So it's safer. You are erring on the side of caution when you take the higher t. No, still go to 40. You notice though the difference between 40 and 50 is very, very small, but it's still erring on the side of caution if you take the larger t. Take the 40, round down. Yep. Okay. Our next example is an investigator wants to know if vegetarians, so we have two populations here, vegetarians versus non-vegetarians. Is there diastolic blood pressure? You know, when they pump up your arm and get those measurements for your blood pressure, is there a difference in the blood pressure between vegetarians and non-vegetarians? Right? Two groups, two samples. So you can see how, I hope you're starting to see with the Etruscans and the Italians, and then the trees, and then the diet and the exercise, and now we have vegetarians and non-vegetarians. There's so many different ways that this problem can be applied with confidence intervals and hypothesis tests. So we can construct the confidence interval for the mean difference of the diastolic blood pressure between the vegetarians and the non-vegetarians to see if there is a difference. Okay, so we would plot the data, take a look at the box plots if you want, and see if there's visually anything, and then we can do these confidence intervals. So a 95, or 90 they want this time. 90, so 90%. So a 90% confidence interval for mu1 subtract mu2. So is what in words, mu1 subtract mu2 in words, just plain language, it would be the average difference in the diastolic blood pressure between the vegetarians and the non-vegetarians. All wrapped up in mu1 and mu2. That's all wrapped up in that notation. All right, so I do, again, I get it ready. I can get it ready right here. X1 subtract X1 subtract X2. So X bar 1 subtract X bar 2 plus or minus RT times our standard error. And I do the standard error over here. You'll see in the formula sheet, the standard error is everything, well, it's right here. It's everything with the square root. So S squared 1 divided by N1 plus S2 N2. Right. And we can just do that in as an aside. And we got to get our t as well. So let's see. What degrees of freedom? If I'm thinking of T star. Yes. 39? Yeah, 39, right? 39 degrees of freedom. So we would take, so 40 subtract 1 gives us 39 degrees of freedom. Our table, though, doesn't have 39. What should we use? Yeah. It won't make a huge difference, but we always round down. So we'll just stay consistent. If we sometimes round up and sometimes round down, then our analysis can be really messy. It's always round down for these and grab the 30. And it was a 90 though, right? This time, correct? A 90% confidence interval. So we're going to get the 90% column with 30 degrees of freedom, 1.697. 1.697. 1.697. That's going to be our t. We need to still get this standard error over here, so we need to plug these in. Plus, now remember, if it does come to you, just keep an eye on those standard deviations. If they come to you already squared, if those are variances, then you don't need to square. You don't need to put the little squares on if they're already squared. Just keep an eye on that, because, and then when I do this with the calculator, I make sure I have lots of brackets. I use all these brackets just to keep everything inside the Radican, and I don't make a mistake. Decreases the chance of an error there, a mechanical error. Oh, I think so 11.7 squared divided by 40 plus 11.4 squared divided by 43. Does anybody have a number? So I think I'm going to grab anybody have a number for that? What is it? Two? Yeah, yes. Anybody else get anything different than 2.54? We're good, right? 2.54. And then I just do this. I go bracket 72.9, subtract 73.5, plus or minus, there's our t, 1.697 times 2.54. 2.54. Make sure we have a point in there so that it gets calculated correctly. Right? So 72, remember we're talking about vegetarians, diastolic blood pressure versus non-vegetarian. So the average 72.9 subtract 73.5 gives us negative 0.6 plus or minus. So you can see because we took the vegetarians and subtracted the non, it looks like the vegetarians are lower because of the order we did that in. And so we can go 1.6 4.97 times 2.54, which is 4.31. So you can use this. It's just if the question says, what's the standard error? You have your answer 2.54. And now we have a -6 plus or minus 4.31. So we need to keep going to see what this result is. So -0.6 subtract 4.31 is equal to -4.912. -0.6 plus 4.31 is going to give us 3.71. So before we go on, did I do that? Okay, yeah, sure. That's part of our formula. It's our margin of error because we're taking into consideration the size of the samples, and we're taking into consideration the standard, like the whole standard error has the size of the samples and the variances in it. So the standard error times the t gives us that plus or minus margin of error. It's part of our formula. For a normal, for one sample? Yeah. Our one sample, if we go back to our one sample, it was x bar plus or minus t star, right? Times s, wasn't it? S divided by square root n. This here, s divided by square root n, that's our standard error. Yeah. So it's kind of neat when you put it all together like this. We go from one sample, this is for one sample, and this is when we have two samples. Right? Does anybody get anything different than this? I ended up with -4.91 to positive 3.71. We're good? So, is there a difference between the two? We're looking to see if 0 is in there. We see a 0, so that means there is no difference between the vegetarians and the non-vegetarians in terms of the diastolic blood pressure. So I can say it like this: 0 is within the interval. And I just need to roll up there. Therefore, there is no difference. 0's in there. The 0 means you take two numbers and you take the difference and it's 0. That means there's no difference. There's no difference. It's 0. So here, there's no difference between the vegetarians and non-vegetarians in terms of the diastolic blood pressure for these data, right? All right. How are we doing? Everyone's sort of seeing that two sample HUD. It's very, very applied, right? So you can look at your snow tires, right? Your winter tires versus your summer tires. How many more miles do you get for each, right? Any two populations you can compare and run these tests. Okay. All right, number 3. Okay, we have a healthcare example. This is what I do. I look at the average length of stay in the hospital, in the average length of stay in the emergency department. I'm working on a study right now for that. And we get lots of data, lots of patients, and we use those patients as a sample. And here we can compare a dynamic system and a static system. So what does that mean? So the number of acute post-operative days in a hospital, using a dynamic system and the static, the data provides sufficient evidence to conclude that the mean or average, right, number of acute post-operative days in hospital is less with the dynamic system than with the static. So dynamic means get up and get moving. Don't just lie. And the static is rest. Take it easy, right? So dynamic, is it better to get up and get moving as soon as possible? They now know it's usually better for us. They used to, years ago, you would be in bed for days. Not good for the circulation, right? So now it's like, as soon as you're able, you get up and you get going. And so we have the dynamic system versus the static system. We have all our data, and we can just run the hypothesis test using the significance level of 5%. And we do this. So step 1, the alternative hypothesis is always going to be equal. It's always equal to 0. You can literally just write it down. So population 1 is dynamic. Population 2 are the static patients, right? So we have 2 different groups of patients. And so the difference between the static and the dynamic will be, it's hypothesized to be there's no difference in the length of stay, right? So this is, remember, this is the length of stay. So we call it length of stay in the hospital after the surgery versus the alternative hypothesis, which is, well, we go back to the question, read the question in your little story, this scenario, and go, well, do the data provide sufficient evidence to conclude that the mean number of acute postoperative days is less? Here's the key word here, less. So that's going to say that the difference is less. So it means that the dynamic system is less than, right? Because it's this here. Another way to write this is mu1 is less than mu2. Dynamic is less than the static. So that means you get out sooner. If you get up out of bed and get moving, they have shorter stays. Potentially, we have to check the whole test to see, but that's what we're testing. Okay. All right, step 2, the test statistic. The test statistic is T. It's going to be x1 subtract x, I don't know why I keep doing the mu, x2 divided by the SE. So it's just the difference in the numerator, subtract 0, and I'm not writing subtract 0 because it's always 0, and then divide by the SE. That's our test statistic. We can do this, the SE. Let's do it over here. I'll do it in a different color even so that we have a different color. So we have here 1.22 squared over 14 plus 4.59 squared over 6. So we only have 6 patients in the static and 14 in the dynamic. So there is a difference in the size of these samples, which is fine, but we can get our standard error over here in the margin. Carefully put those into your calculator. Make sure your calculator is working and it's doing everything we need it to do. So 1.22 squared divided by 14 plus 4.59 squared divided by 6. And so what do you get for the standard error? Again, any of these questions could be, any of these pieces could be a question, right? So what's the null and alternative hypothesis? What's the test statistic value? What do we get? Anybody have a test statistic value? Anybody over here? 1.90? Or how about 1 point, yeah, we could do 1.90. It'd be close. How about 1.89? Will that work too? Or no, I guess 90 is better. Right, because I end up with 1.88995. So I could go 1.89. It's going to be close enough. 1.89. Just keep it off to the side. If it's a show your work though, keep it in the box, right? Because you want to write in the spaces underneath your questions, right? So that I can see it. Don't put anything in the rough work because I might not see it. So the difference is 7.36 subtract 10.50 divide by 1.89. Right? So I'm going to get that difference. 7.36 subtract 10.5 divided by 1.89. I get negative 1.66. 1.66. Now I need to get a p-value range from my t-table, and so I need to know how many degrees of freedom. How many degrees of freedom would I use for this question based on everything we've talked about this morning? Degrees of freedom? Yes. 13. 13? And so it would be 14. Is it the smallest of the two? Yeah, so so we have two groups. You're seeing it now. So we have two groups. There's group 1, group 2. So degrees of freedom are going to be, what will they be? 5, yeah. So we take the 6 and go 6 minus 1 equals 5 degrees of freedom. That's going to give us a T star on 5. We want 5. So we want to, well, we're not going to get a T. We're going to look this T up here on 5 degrees of freedom. And that will give us our p-value. So our range, our p-value. And this is a one-sided test. And so if we go 5, so we don't have any negative values. We just take the positive. So 1.66 falls where? So we're looking for t equals 1.66. Where would that fall in that, in this row? 1.66 is where? Between the first column and the second column, third, it's a 60 and 70, the 70 and 80, 80 and 90, right? In between those two. So it's in between, 1.66 would be in between these two. And so what we do is we scroll down to the one-sided p. It's right here. It says one-sided p, and we get those two values. There they are right there. So the p-value is between 0.05 and 0.1, so between 5 and 10%. We go back and we go, the p-value is between 0.05 and 0.1, right? I'll just do that. So which is less than, sorry, it's not less than, it's greater than alpha, which is 0.05. So if a number is between 5 and 10%, and your cutoff range alpha is 5%, so what can we conclude based on that? Since the p-value range is greater than alpha, what do we do? Reject or not reject? It's going to be, it's a binary answer, right? It's one or the other. What are we going to do? Right? Just keep in mind, we need a small p-value to reject. Do we have a small p-value? Is it less than our threshold? No. So we cannot reject. We cannot reject, right? So we cannot reject, which is really going against our intuition for this question, because we really thought we were going to and conclude that it's better to have the dynamic system. But I think there's issues with this example where we only have 6 patients for the static system, and the dynamic system's more than double that. But we cannot reject the null hypothesis in this case. And we conclude that there is no difference. Okay? Get more data. What do? We get more data. We get a much, much larger sample size. Usually we have thousands of patients for each group. But you get the idea. You know how to make the conclusion if it's, right? So just to remind everyone, we reject when we reject the H-no when the p-value or the p-value range is less than alpha. Yeah. Is exactly. Oh, so the number, like if you pick like what if it was between 2 and 5? Your p-value is, but hold on, is your p-value a range, or you mean your significant value is 0.05? So if my range, let's do that as an example. If we have an example here and our p-value range is what? Okay, so alpha is 0.05 and the p-value range is? What would we do? Pick a number between 2 and 5. So it's always, so here we would reject, because the p-value is any number between 0.02 and 0.05. We reject. We would reject the null hypothesis in that case. Yeah. And whenever we reject the null hypothesis, the test is automatically statistically significant, okay, at the 5% level or whatever level your cutoff is, right? All right. And we have one more question. We'll conclude with this one, and then we'll take a break and come back for the final exam review. So do we need to do a test for this? Do women talk more than men? So they actually do studies on this. So a series of 6 studies investigated the number of words women and men speak per day. And I think this example is even in the textbook. So they do studies on things like this, and the results for one of them is given below. This is for one of the series of the studies, the 6 studies. And we have here, we're going to conduct a hypothesis test to see if there's a difference. So we have 27 women, 20 men, and you could sometimes, when I see this, I see instead of 1 and 2, I see X subscript F and X subscript M for males. Sometimes you'll see different subscripts denoting, right, the different groups. So long as you know how the groups are, where they're coming from and which population belongs to which. So group 1 is the women, group 2, population 2 is the men, and we're going to conduct a hypothesis test. So we have average number of words for women was 16,496 words, 0.1 words in a day. Average for the men was 12,866.7, so considerably less. So we're already suspicious we're going to have a different result here. But we have to take into consideration the standard deviations and run the whole test. So let's do it. So 1, we're testing that there's no difference. So the average number of words for women, subtract the average number of words for men, is 0. We're saying no difference. Versus, we're going to see if women talk more than men, we're going to go mu1 subtract mu2 is greater than 0. So that's the same as saying mu1 is greater than mu2. That means that the women speak more words per day than men. So we do the test statistic. It's just going to be T equals X bar 1, subtract X bar 2, divide by the standard error. Again, I'm going to do the standard error in the sidelines. I'll do it over here. And we're going to go, these are big numbers. So 7, make sure I have enough room to fit this in. I'm going to just move over a little bit more to fit this all in. So 7914.35 squared over 27 women plus 8342.47 squared over 20 men equals. So carefully put this into your calculator and see if we all get the same. It's 27 women, 8342. I'll give you a moment to see what you get. Anybody have a standard error for me? Because we're doing number of words spoken per day. These numbers are quite large. We're in the thousands of words. Imagine, though, our average number of words we speak, 16,496, is a lot. Anybody have a standard error? Standard error? No, not yet. We're trying to get this number right here in the orange, because it's so much easier to calculate the test statistic. If you do this in pieces, you just have to remember these are intermediate steps that are going into a formula. So you need to carry at least, 2, 3 decimals or more if you can. Anybody have a standard error? Yes? I get a 2, but I get, oh yeah, 2004-08, is that what you said? Yeah, I get that too. Thank you. Yeah, these are big numbers. 2,408.262. How's that? Okay. I think it's the largest standard deviation we've had in the entire course. But then it's comparing the number of words we speak per day, right? So that would be the standard error. So let's go back to our test statistic and let's get that calculated. So these are really large numbers. So 16,496.1 for the women, subtract 12,866.7 for the men, divide by our standard error, 2408.262. Carefully get all those in to your Wow. Wow, it's going to boil down to a, what are you boiling it down to? This really boils right down to a nice t-value. It's like standardizing it, right? We're like getting a t-score here, really, right? Were you able to boil it down? Anybody have a number? T? Test statistic. So this could be a question too. What's the value of the test statistic? You have a number? Yeah, it just boils right down to 1.507. How about 1.51? Is that'll probably, I guess we can keep the 0.7. We're using the t distribution. It goes up to 3 decibels. So yeah, boils right down to 1.507. Small, now all those words and then that. So we need to then think about how many degrees of freedom. We need to get the p-value. And remember, this is a one-sided p-value because it's one-sided because we're looking at greater than, right? So it's going to be between, and we need how many degrees of freedom? Anybody want to guess what the degrees of freedom is for this question? Yes. 19. Yes. So we take the smaller of the two. There's less men than women. We have 20. So 20 subtract 1 equals 19 degrees of freedom. Let's go to the table and find this value here, 1.507 along that row. We go over to 19 degrees of freedom right here. 1.507 was our value. We want to see where that would fall. And I think it's falling between these two values, right? You can take a double check, make sure it falls right. 1.507 is falling in between those two values. I just scroll down and it's the same p-value range as our last question. I've already got it highlighted. So they correspond to these values here, 0.05 and 0.1. That makes sense? 0.05 and 0.1. So let's go over to here, 0.05. Well, this is sort of a disappointing result. I'm just checking it. I'm checking it because can we reject and say there's a difference between the number? It's kind of funny, isn't it? I was hoping for the women to be more, but yeah, we cannot. So this is greater again. This is greater than alpha. So therefore we cannot reject. And we conclude, right? So the p-value range is greater than alpha. And then we cannot reject. And we conclude that there is no difference, statistically speaking, maybe practical difference, but statistically there's no difference, at least with these data. Remember, this was a series of 6, and I think the textbook shows all the different studies. So with this data, there's no difference between the two. You can see, though, if we just looked at the averages, we would absolutely conclude that there's a difference. But because you have to take into consideration the standard deviations and the size of each group to keep it fair, right? Apples to apples, you standardize them, and right? Then you can run the test fairly and using statistics, we can conclude there's no difference.